In this video, we're going to learn a little more terminology about the derivative. If f prime of a exists, then we say f of x is differentiable at a. Differentiable is just our word that will mean you can find a derivative. Otherwise, we say f of x is not differentiable at a. So we'll expand on that just a little bit. If f of x is differentiable for all of the x values on the interval a comma b, an open interval, the interval that goes from a to b but doesn't include either endpoint, then we say f of x is differentiable on AB. Just giving us a shorter way of saying that f is differentiable for all the x's on that open interval. F is differentiable on AB. Now I want to look at what we could say if I was looking at a closed interval rather than an open interval. Let's say I have a function that's defined on the closed interval a comma b, and I want to talk about f's differentiability on that closed interval. We say f of x is differentiable on a comma b if, well, to me there are three things to consider. You have all of the points on the inside that would be from the open interval we just talked about, and then you have the two endpoints. And the two endpoints are the only things that are a little bit weird, right? Because so far as this function is concerned, I can only get to a from the right, and I can only get to b from the left. So for f of x to be differentiable on this closed interval, what I'm going to say is that f has to be first differentiable on the open interval. And now I need to think about those endpoints. So to think about those endpoints, I need to think about what my tangent lines look like as I get close to that point, right? So maybe I draw a secant line first, right? And that just looks like a good old a plus h, right? And I can let a plus h get close to a, but only for positive values of h. There's nothing over here. Well, that would be a limit as h is approaching 0 from the right, the positive values of h. And then calculate a derivative, a one-sided derivative. So if I can draw a tangent line there, just thinking about what these secant lines do as I come in from one side, that's going to be okay. And so now I need to think about the other endpoint. I can't draw a b plus h out here. It would have to be here. Oh, and that looks very funny, right? B plus h being before it. And I guess what I'm thinking here is h would have to be smaller than 0. And, well, that would mean my h value is approaching 0, but from the left-hand side. Those values of h that are close to 0 but negative. All right, and then that would be a derivative on that side. All right, what I have here is a statement that says, hey, if I'm differentiable on the open interval, and I'm differentiable at the endpoints considering the appropriate one-sided limit, this is a right-hand derivative, and this is a left-hand derivative, then I'll be differentiable on the closed interval. If I was to think about one of the interior points, let's call it C. Both of these statements would have to be true, right? I'd have to have the two-sided derivative. My secant lines coming from this side have to go to that tangent line, and so do these. A one-sided derivative just considers either the left or the right. All right, let's look at an example. And this is an example of a function we've already taken a derivative of. Y equals root x. We did this one using the alternate definition of the derivative. So in this video, I'll use the original definition of derivative. It's always nice to do a problem multiple ways. All right, so I'm going to do the trick where I multiply the top and the bottom by a conjugate. On the bottom, I'm just going to multiply the two things together. All right, and on the top, the middle terms cancel, and I get an x plus h minus x. Plus x and a minus x, those will cancel. All right, I can cancel out the h's, and as h tends to 0, I have root x plus root x. Give me 1 over 2 root x. All right, let's think about the square root function. If I was to graph the square root function, we'd get a picture that looks like this. The derivative, the slope of that curve at every value of x is given by this. Well, my original function has a domain, x bigger than or equal to 0. Very clearly, this formula will only work for x's that are bigger than 0. And I'm very curious what happens at 0, and that is an endpoint in the domain. If I'm going to try to calculate the derivative here, I need to be taking a derivative from the right-hand side. So let's do that. So y is equal to root x, and I want to find y prime of 0. But I only get to approach 0 from the right-hand side because of the domain. And better said, I only get to approach, h only gets to approach 0 from the right-hand side because of the domain. Right? 0, coincidentally, is my x, and then 0 plus h would be this other value out here. H can tend towards 0 only from the right-hand side as those 2 points get closer and closer together. All right. Just taking my limit. This simplifies fairly easy. And looking at those powers of h, I get that. And as h tends to 0 from the right-hand side, the bottom tends towards 0, the top stays as 1. This is an infinite limit. Y prime of 0 does not exist. Right, because those infinite limits were a special kind of does not exist. Well, let's look at our tangent lines. So I could imagine finding the slope at 4. Y prime of 4. I can just use this function. 1 over 2 times 2, that's 1/4. Put in an x, get out a slope. That's what the derivative does. All right? I could imagine finding the derivative at 1. Get 1/2, a steeper slope, right? 1/4 slope, 1/2 slope. And in fact, as I get closer to the origin, these lines, tangent lines, are getting steeper and steeper, as if when I get right here, my derivative is undefined because I would need a line that was infinitely steep, like a vertical line. All right, in our next video, we'll finally talk about all of the different ways that derivatives can fail to exist. But just to kind of summarize, in the past 2 videos, absolute value didn't have a derivative at 0, and it made a V shape there. And then the square root function doesn't have a derivative because it was trying to become, its tangent lines were trying to become vertical there. So both of those things should come up in my next video. Things that look like this and things that look like this. See you then.